Hello, today I'll be making a video on forces. Today we'll be going over the three of Newton's laws, as well as doing some applications and examples within robotics. Of course, a force is equal to mass times acceleration, measured in newtons, and it's basically a mass being accelerated, which goes into Newton's first law, that being that, what I like to call the law of inertia, that being that any object that is acted upon, any object currently in motion will stay in motion, and any object currently at rest will stay at rest until acted upon by an outside force. We call that I like to call it the law of inertia. Now the second one is the more straightforward one. That's the equation. We have force is equal to mass times acceleration. The original idea here that Newton had was that force is what's called proportional to acceleration. Within all states where we have a constant mass, we have that force increases as acceleration increases in the same way. However, we're able to find it by a force is equal to the mass times the acceleration. Number 3, every force has an equal and opposite force. So as long as you're not accelerating, any force that you apply will have an equal and opposite one. The best example is if right now you are standing up, and right now you have the force of gravity acting on you, but you also have a normal force exerted from the earth onto you, which is equal and opposite to that. Let's get into some examples. In many cases when you're doing examples, you will ask, and you're able to make equations in your coordinate system. We'll be using a very simple XY coordinate system for here. Let's start off with a more simple question, then we'll do a more fun one. Starting with here, let's start off with a fun spring problem. It's kind of tying into the simple harmonic motion problem. We have a spring here with a mass, say m. Let's do a symbolic question. Hung up here onto the ceiling something. Now if we're going to make a free body diagram of this mass, free body diagram needs to have 3 things. It needs to have a coordinate system, needs to have distances, which in this case isn't really applicable, and it also needs to have forces. This one's going to have 2 forces on it, that being the force of gravity and then the spring force. As I said in the other one, this force of a spring is equal to the spring constant times the distance that is extended, which will be this distance here, at equilibrium. Let's make our sum of the forces. So if I were to ask you what the sum of the forces in the x is equal to, are there any forces acting in the x? There are not. Sum of the forces in the x is equal to 0. However, in the y we have a little bit of a different story. This is just the notation I use for writing forces. We have 2 forces. Since we have y positive up here, we have that force, the spring force, minus the force of gravity. And let's state here that this isn't accelerated. It could be going under simple harmonic motion. However, it is not accelerating. Let's make this equal to 0. Say we know m, but we're solving for what x, this distance, is. We know that kx is equal to mg. Now we know that x is equal to mg over k. That's one simple example. Now let's go on to another one. This other example we'll be doing is going into a more robotics example, or an application, and then going into what happens when sum of the forces is not equal to 0. As we know, things that are in motion will tend to stay in motion. As part of number 1, we'll know that as long as it's not acted upon by an outside force, an object will continue to move with the same velocity for as long as it is moving as such. However, when you have a force acting, it can accelerate, and whenever you have that sort of acceleration, you will have a change in the velocity. So let's say we have a robot, and it is trying to, say we have a rover. I'm not very good at drawing, but let's picture we have a rover. It's trying to push some boulder, some other object, in this direction. And it's accelerating at 3 meters per second squared. Let's think about what forces we have acting. We have the force of gravity, as well as what we call a normal force acting up on it. And we will see why we have a normal force. One other thing we have in this case is a force of friction acting against. So we need to find this force F here in order to move it at here. What we know about friction, the thing for friction is equal to the normal force times the frictional coefficient, where we'll say that the frictional coefficient of this thing moving is equal to 0.2 and is a unitless coefficient. Now, a lot of the times when you're solving for the normal force, you will have something like here where it's equal to gravity. However, there can be some cases, like for instance, had this been at an angle upwards, we could have said the normal force is equal to the gravity minus that upwards component, as normal force will not always be equal to gravity. However, as we know that this thing isn't accelerating in the y, normal force is equal to the other components to make some of the forces in y equal to 0. Sum of the forces in the y equal to 0. We have mg is equal to the normal force. Mass, let's say, is equal to 10 kilograms. 10 times g is 9.81. We have n is equal to 98.1 newtons. Now we know friction as well. Talk about our sum of the forces in the x. The sum of the forces in the x is not equal to 0. Rather, is equal to some value ma. Well, we know what m is. What are the forces? Well, it's F that we now know, minus the frictional force, which is N, which is 98.1 newtons, times friction, which is 0.2, is equal to m times a, which is 3 meters per second squared. Pardon this here. Now we have F is equal to 10 times that 3, which makes it 30 newtons, plus that 98.1 times that 0.2, and what that will give us is 19.62. With that 19.62 plus 30, we end up with that F, that force that we were trying to solve for, is 49.62 newtons. That'll be an example there. Now, there are hundreds of problems you can do with forces. They are very well versed. There's only that one equation as well that you need to know. And these are just 2 examples. Thank you for watching.